Hello everyone, welcome to the second part of an To Be Astronomer reacts to a geocentrist movie, The Conclusion. Last time we talked about all of the methods and that surround this so-called documentary, and today we will talk about the science that was heavily misunderstood, and I would like to start by the Michelson-Morley experiment. Before I do that, just a quick note, I have a throat infection, so sorry if my voice sounds a bit rough today. Alright, so the Michelson-Morley experiment, as you can see here, consists mainly of a light source. I draw a light bulb there. It's not really a light bulb, of course. It should be a coherent source of light, right? Not something as dirty and as incoherent as a light bulb. And note that these two are not two different colored light beams, but I just colored them in depending on the path they take, right? So that it's more clear what I'm saying. You have a light source and it emits light, and one of these beams kind of goes through this beam splitter, which has semi-reflective characteristics, if you will, and part of that is being reflected down towards this mirror, and it comes up, then it gets not reflected because, again, I said semi-reflected, so the other part is just being transmitted. So it passes through the beam splitter and it enters the detector, and the second beam passes straight through the beam splitter because, again, it's semi-transparent. It comes through, hits this mirror, comes back, and now goes up to the detector, right? And these two distances from beam splitter to mirror are of equal length. Okay, and now so in the end, if the light source was coherent enough and we have monochromatic light, these two light beams will be in phase, right? So you can not detect any kind of phase change between the two. Okay, so that's a Michelson interferometer. And one of these Michelson interferometers was used in the Michelson-Morley experiment. The idea was, well, if there's an ether in any direction, one of those beams, in this case the green beam, which is not green but I colored it green, would travel at a different speed than the red beam, and at the end in the detector they had to be out of phase, right? Now the problem here is that, as you're probably aware, the Michelson-Morley experiment yielded a negative result. They could not detect any substantial change, especially not one that would coincide with ether, right? There was, of course, noise and uncertainties in the measurement, but with every scientific measurement you have that, so that's not a surprise. Still is a negative result, right? So yeah, so that's essentially the Michelson-Morley experiment, right? And the idea was that you had the Earth here and an ether, in some direction, right, relative to the Earth and relative to the measurement device that was set up in a given way. So when at first they had a negative result, they thought, okay, maybe, right, it's possible that right now when they did this experiment, they were relative to the ether in a way that allowed those two light beams to be modified by exactly the same amount. This possibility is incredibly small, but Michelson-Morley, being as honest as they were, said that it is possible. It's unlikely, but it is definitely possible. So what they did is they turned it around a couple of times, the measurement device, and couldn't find any deviation from that, right? So the only other possibility that was now possible, and which is almost ridiculous, right, is that this ether field thingy is stationary precisely where they tried to measure their experiment. So in the course of human history, this experiment was repeated a couple of times at different locations around the Earth when the Earth was at different orbits around the Sun. So the chances that each time the ether was precisely addressed where they measured it, when they measured it, are so non-existent that this is very much special pleading if you want to invoke that, right? Okay, so what do flat earthers misunderstand? Not only flat earthers, clearly also the people in this documentary misunderstand about it. If there was no ether, which there isn't, those two will always be in phase in the lab frame, clearly, because the two people that are observing that are in the lab frame, you know. So light here is always in phase. It simply cannot detect motion if there is no ether. It cannot detect motion in the reference frame, right? So Earth could be zooming about with half the speed of light. The Michelson-Morley experiment will look the same. It has no way detecting anything without an ether. And it should not detect. That is important. Everyone who thinks that the Michelson-Morley experiment somehow disproves the motion of Earth around the sun, it should not detect the motion of Earth around the sun. Tell me where. This should detect Earth's motion around the sun. It shouldn't, and it can't. How would it do that? Explain it to me. This is extremely poor understanding of the Michelson-Morley experiment, and the fact that apparently in this documentary someone who, as according to my research, has a bachelor's in physics and who explains that this disproves the Earth's motion around the sun is so ridiculous to me that it makes me wonder if he found his bachelor's degree, as I mentioned in the previous episode, at the bottom of a cornflakes carton. It's completely and utterly ridiculous, right? No understanding for the Michelson-Morley experiment whatsoever from that side. Relativity. Relativity is a difficult subject for geocentrists as well as a bunch of flat earthers, as I've recently heard. First of all, they really love because they are visionist, right? History isn't the way that we, whoever we are, say that it is, because then they would look bad, I guess. So what you really need to do as a flat earther, as a geocentrist, is you need to have a severe misunderstanding of the origin of relativity, because they say that it was like kind of a patch to fix up the ether, to get rid of the ether, which is completely wrong. Ether at the time, even of James Clerk Maxwell, so a solid 40, I believe, years before Einstein came up with relativity, was already kind of in shambles, right? The mechanical properties of ether were essentially magical. It had to be a fluid because it needed to fill all the space. It needed to be much more rigid than usual materials you can see on Earth to support all of the frequencies of the light waves. It had to be massless and had absolutely no viscosity, because else it would influence the orbits of planet. It should be completely transparent, incompressible and continuous, even at the smallest possible of scales, because light doesn't really behave different on small scales. Not yet quantum scales, mind you, but like very small scales, like let's say at a millimeter, right? So it's completely ridiculous. Maxwell actually wrote at the time, he wrote that, and I quote here directly: "Ethers were invented for the planets to swim in, to constitute electric atmospheres and magnetic effluvia, to convey sensations from one part of our body to another, and so on until all space had been filled 3 or 4 times over with ethers. The only ether which has survived is that which was invented by Huygens to explain the propagation of light." So even at the time, people were more looking down on ether. It was just a thing that everyone, like, kind of, it's your go-to thing when theorists at the time didn't know what to do. They just say, "Oh, there's an ether there," right? So okay, enough about ether. The thing that they did a few times in this movie is misunderstanding reference frames, not just in relativity, right, but like more in general. And I'd like to explain that with an example. Here you have, at the start, you have a small, poorly drawn spaceship next to a equally small, equally poorly drawn drawn, asteroid. Supposing that there's nothing else in space. And now, these two cases, when it comes to the physical laws that act in relativity to them, right, are the same. Case 1, where we look at the spaceship as stationary, and case 2, where we look at the asteroid as stationary. Within relativity, these two cases must have the same physical laws still active on them, right? The length contraction, for example, doesn't care if one is moving away from, if the spaceship is stationary or that the asteroid is stationary. The length contraction, for example, within relativity doesn't care, right? But that doesn't mean that these two are equally as valid. Of course they aren't. You put an observer on the spaceship, you put an observer on the asteroid, right? One on the spaceship, one on the asteroid. And one of them is going to experience a force, the other one isn't. So clearly, the spaceship is accelerating and moving away. What relativity is trying to say is that within relativity, the effects of relative motion, special relativity if you will, the effects of relative motion do not care which of those two objects is moving away. That's the thing that relativity says. That doesn't mean that one is just as explainable as the other, right? It's like when they say that, just for observation's sake, it would still be the same if Earth was at the center and the solar system is moving, the rest of the solar system is moving around the sun. For observations, I agree, that wouldn't make a difference, right? But that doesn't mean that it is that way, because the rest of the laws of physics still apply, and those make it impossible for the Earth to be in a central place where the sun revolves around it. Just because you say, well, observations will still be the same, that doesn't mean, that's not an argument for it. That's just not an argument against it, right? So completely ridiculous. And the last thing I would like to talk about for today is the Sloan Digital Sky Survey. Now, funnily enough, I have started my term, right, my astronomy term a few weeks ago, and I now have extragalactic astronomy. And one of the first things that we talked about was the Sloan Digital Sky Survey at university. So after the class, I walked up to our lovely professor and I asked him, well, Professor, I'm sorry, I have a question regarding the Sloan Digital Sky Survey. He was, yeah, sure, go ahead. Well, what do you need? And I said, well, I have heard that some people say that there is some kind of big structure within the galaxy distribution of the Sloan Digital Sky Survey. Do you know anything about that? And he said, well, at first, I must admit he didn't understand what I wanted. So I re-explained it. And he said, well, there are certainly regions that are where there are more galaxies, for example, this one right here. And there are regions where there are less galaxies. He pointed at this one right at the back, although he said that because it's so kind of far back that for the telescopes that were used with the Sloan Digital Sky Survey, that's not a big surprise that towards the back that we expect less because they are fainter galaxies, right? But he said that apart from that, there is no, like, if you will, global absolute structure. And when I said to him that there was a ring structure, I didn't tell him where the sources, like what the sources were from that, right? I just told him that I have heard that some people say that there is a ring structure within the Sloan Digital Sky Survey with the galaxy distribution, right? And he said, well, he's not an expert on the Sloan Digital Sky Survey itself and at galaxy distributions. He's focusing more of the observational side of galaxies, right? He would never have heard of that, and it would surprise him that he hadn't heard of such a big thing, really. And I completely agree. I've never heard of that within astronomy. And the thing that they say right here in this picture, this is the official picture, by the way, from the Sloan Digital Sky Survey. I pulled it directly from their website. This is the picture that they give, right? Please feel free to draw your circles in this one. The only one that you can do is this one right here, right? I agree. even though it wouldn't be a circle because this line here is clearly more dense than that one, so there's not a real circle right here. Right back here, I don't think there is a circle. There are regions of higher density right here, but they aren't here. They are definitely not here, and those make a nice circle. They don't make a nice circle because you can see if you drew a circle right here, the radius here, right, would be much less than the radius right here. So it's not a circle. The center would be somewhere here, I believe. The same goes for the backside, if you will. There are no circles whatsoever. Completely ridiculous. And neither I or apparently my professor for extragalactic astronomy, mind you, has ever heard of that. So, in the end conclusion, they misrepresented and misunderstood pretty much all of the scientific points that they say, that they list in the documentary, none of which are inherently supportive of a geocentric model in the first place. I give this movie about, let's say, 2 out of 10 points for the methods, because they had a few scientists in there. We're not going to be talking about, I already talked about how they ended up in there, and then it was a huge setup, and they still get 2 points for that. For the scientific part of it, they get 0 points. Horrible movie, horrible message, and I cannot believe, right, that flat earthers cite this movie as evidence, even though it is so easy to look into how this movie came about, how dishonest the people in it were, and what the people that appeared in the movie said about the movie after the fact. The only thing that you could really say to get rid of all of these problems on the flat earth side is invoke conspiracy. And as I said so often within this movie series, and I'd like to end it on this very note, if you have to invoke conspiracy, the idea you're proposing is probably crap to begin with. And with that, thank you so much for watching, and I will see you in the next video that I eventually do. We'll see. Have a nice time until then, and do all of the YouTube things that people do, if you would be so kind. With that, goodbye, and thank you for watching.